All right, welcome everyone. My name is Sharon White. Welcome to today's webinar, Understanding Verification for Digital Design. Before we get started, I just want to take a few minutes to introduce our speaker, BLT, and to go over some housekeeping. A few notes: if you have questions, please put them in the chat panel. We will get to them during the Q&A at the end. Today's webinar is being recorded, and we will send the recording out once it's ready. It takes about a week, so look for it early next week, all right? There are no books or slides provided with today's talk. So first, let me introduce to you BLT. BLT has been in the engineering design services business for over 30 years. We were started by one of the original Xilinx FAEs, and our headquarters are in Maryland, and we also have an office in Melbourne, Florida as well. We design chips, boards, software, and complete systems for commercial, military, and intelligence clients. Our designs are in space, undersea, and everywhere in between. And we've been teaching AMD Xilinx training for 25 years. We're an AMD Premier Partner and an authorized training provider. Our training is by engineers for engineers, and we bring our decades of real-world design experience to the classroom. Our speaker today is Cole Smith, project engineer here at BLT. Cole's expertise is on RTL design and verification with FPGAs. In his career, Cole has focused on verification and design on software-defined radar, defense systems, and industrial network systems for commercial and defense clients. He's not sitting in front of his when he's not sitting in front of his computer, Cole likes to get out and go rock climbing and snowboarding. And if you'll indulge me, since I'm the marketing manager, I wanted to let you know about some upcoming opportunities we have here. If you're interested in learning more about verification, we have classes on Verilog and SystemVerilog coming up in October. Cole is going to be teaching both of those, and I will put links to those in the chat panel for you. We're also running a BOGO special until October 15th. So if you register for any of our classes that are in 2023, you get a second class from a list of qualified classes that are for you or your colleague to attend. So I will put all of that information into the chat panel for you. And if you're interested in more webinars from BLT, we have our 4-hour no-cost workshops, and you can check out all of that information on our course calendar. Again, I'll put that link into the chat panel for you. Some of our upcoming topics include AXI, RF SOCs, CREA-SOMs, and debugging. And next week, we have a webinar on outsourcing. So that's a little bit different from the typical stuff that we do. So if you do have questions about our training, classes, or other services, our contact for that is Lisa Weaver, and I will put her information into the chat panel for you. So I know that's a lot, but I'm done, and now I will pass it over to Cole to get started on verification.
Hey everyone, good afternoon. So as Sharon said, I am going to be talking about randomization today in your test benches. So randomization is something that is widely utilized in verification. It's extremely capable, and it can take your test benches to the next level and really give you a next level of confidence as far as your design functioning correctly and as you expect it. I've seen cases where people would try to utilize randomization through other coding languages, like they may have a Python test bench or a C test bench that's going to do the randomization and then supply those values through some like text file or something to a SystemVerilog test bench, when you're actually capable of just avoiding that kind of altogether by just doing the randomization through SystemVerilog. That was one of the things that they really emphasized when they created SystemVerilog as a language. So just want to highlight those things so that way you guys can kind of learn about them and see how to utilize them, which I'm going to show in the demo. So for the topics I'm going to talk about, we're going to go over when and where to use randomization. We're going to talk about stimulus generation and auto checkers. So when you are generating randomized stimulus for your test benches, it can be quite a pain to verify those values and your outputs by hand, especially when you're working with large data sets. So you want to build auto checkers that are going to kind of run the same operations in parallel and then validate the data when your module when your module outputs the data. And then after we talk about stimulus generation and auto checking, we're going to go over SystemVerilog randomization. So then how you can actually write code to do these randomization methods. And then we're going to go over, or I'm going to do a live demo for you guys, kind of showcase some code, some more in depth from the randomization slide, show how these methods can be utilized in a real world test bench. And then after that, I'm going to be answering your guys' questions if you have any. So um, I look forward to any questions that you guys have at the end. And so yeah, with that, we're going to get into when to use randomization. So there's four main points for four main arguing points for using randomization when you have inputs with large data ranges. So if you have inputs that could range millions of values, once you get up into the 20 and 30-bit inputs, especially with multiple inputs that are of that size, especially with like math pipelines and that sort of thing, you want to make sure that you're covering as many bases as you possibly can. And I know that it can be quite a pain to code these situations and these randomized inputs by hand. You can do it in small cases, maybe if you're using 10 input sets or something like that. But once you start or adding more test cases and more iterations of your tests, the randomization is going to be much more handy, especially because it can kind of get rid of that bias that's created by the engineer who wrote the code. I know in a lot of situations, I will think that I've covered every single case for my test cases, and then I'll move to randomization, and it'll actually turn up that the randomization has covered a situation that I missed because it's pretty easy to think that you've covered everything. So then multiple inputs with many configurations. So if you have a complex module with like 20 to 30 different inputs. Maybe some are just toggling capabilities, and maybe others are completely swapping the configuration, or maybe even like the coefficients of your calculations. So then we want to use randomization there, so that way we can randomize all of our inputs, or the ones that make sense, so that way we can try to cover all of our bases in tandem with each other. When we have complex edge cases, so randomization is going to help kind of cover those complex edge cases. So it may, I know that I've run into situations where randomization caused a calculation about halfway through my pipeline to cause a rollover or something similar to that, and the original inputs didn't look like they were causing any edge cases, because they were well within the range of their values. But because of a very specific rollover or something like that, randomization can help you cover that. And then also with regression testing on these larger projects, especially when you're working on projects that involve ASICs, that sort of thing, regression tests are very common. They're going to just be repeated tests that run automatically, potentially overnight or 24/7, depending on how you set it up. You may have some simulation server somewhere. So when it comes to regression testing, actually one thing that SystemVerilog supports that is extremely helpful is seeding your randomization. So when you seed your randomization, you can save off that value, and you can actually report that as part of your printout, and then use that seed to reproduce your test case. So if you have a test that fails at like 4:30 in the morning, potentially, or uh, chances are there's not going to be anybody there to kind of check that failure, and you're going to miss out on potential tests that could have been running from 4:30 on. So then you can set up a system where your regression test prints out all of the relevant randomization information overnight, or I'm sorry, when the test fails, and then you can use that to reproduce it in a controlled setting, and then look at um, the uh, issues. One thing that's important with that is you can make changes to the RTL, but if you make changes to the test bench, then it's going to potentially change how that seed affects your randomization. So that's actually due to something in SystemVerilog called random stability. So SystemVerilog has a deterministic method of creating random numbers, and they're going to be independently seeded, but they are going to appear in a specific order. So that order is actually determined by objects being created. So that's things like classes, maybe variables being randomized. All of those are going to change the order that your random numbers appear in. So your random numbers are going to be repeatable as long as you haven't caused any more objects, threads, or random numbers to be created before the end of your current test bench. So you can add things on to the end and it will still have a reproducible randomization up until that point. But if you add something into the middle, then it can kind of throw things out of order. So some simulators will actually have a flag that you can add in your run command that's going to set the initialization RNG value. So then that's basically going to be the base RNG value for the entire test bench. So then you can also use the initialization RNG to add either another level of randomization to your test bench, or you can use that as your base for the um, you can use that as your base for um, the regression testing, that sort of thing. So then as far as where to use randomization, we're going to use it in our test bench. In our test benches, it can just look as simple as just a single call. So you may just call standard randomize on a variable. You may randomize a class. It can just be inline. One place that it's going to very commonly live is stimulus generators. So our stimulus generators are something that we can set up that's automated. It's going to create stimulus for our module. Sometimes it looks like a module. Other times you can create it as a task or even an interface. And it's just going to, we're going to code it such that it contains all of the constraints on our data set. So that way we can guarantee that we're not providing any incorrect data, or if we want, we can code it such that it'll provide incorrect data. And then we can verify that our system will handle things correctly. And then also in functions and tasks. So functions and tasks are useful for just like maybe a quick and dirty solution, or also for some more complex things where you want to generate large sets of data, or multiple sets of data that will be used elsewhere in a test bench that isn't necessarily related directly to an input of a value. So it has a lot of use cases there. As far as our stimulus generators go, like I said, we can implement them using interfaces, modules, and tasks. Interfaces and modules are going to be kind of more our formal efforts, whereas with tasks, they're just going to be relatively simple and straightforward. If you start to get them, or if they start to be a significant amount of lines, I often take a step back and kind of think about making it into a module or an interface. One thing that makes tasks really useful for stimulus generation is forking the task, and then you can kind of call that at the beginning, um, and it will monitor some signals and then operate based off of those signals. So you can kind of create like a secondary control module. We can also generate, or our stimulus generators can generate stimulus once. So maybe we can do it on a call by call basis. So if we just have a member function to our interface or our module, we can kick off stimulus generation through that, or we can have it continuously going. So maybe once we turn it on, it will just generate stimulus until we turn it off. One thing that's important with randomization is it can be difficult to debug situations. So I advise using predictable patterns for your debugging in the initial stages. And then once you have like that 95% confidence, we're going to move on to randomization to really be thorough. So with our stimulus generators, it's kind of taking everything out of the designer's hands and putting it into just the tool's hands. The tool is doing all of the data generation for us based off of some code that we've written. So using that, or knowing that, we want to create auto checkers. So again, these auto checkers, they can be done using interfaces, modules, and tasks. We can have assertions and assertions embedded in our interfaces, so that way they are just always checking no matter what, especially when you're working with protocols. And then also we can implement functions that will just check data every single time it comes in. We can potentially load those modules and interfaces with the data that was the input, and then verify that the calculation was done correctly. So our auto checkers can kind of take two paths. We can either verify data formatting, so making sure that our data is within a specific set of ranges if we're working with packetized data. So making sure that we have, or if the packet involves like the IP address, just making sure that the fields are within the given ranges that we are either sending to or from. And then we can also validate like the validity of the data. So then that's actually recalculating the data in parallel and then comparing the two. With our auto checkers, this is often where you're going to print whether you find an error. Sometimes if you want to be extremely thorough, you can print out whether data is passing or not. So uh, with the auto checkers and their print statements, they can really reduce your time needed to analyze a failure in your test, because you have the data printed out very nicely and neatly for you, as opposed to having to weed through some waveforms to find an issue, which can definitely be difficult. So then going on to how we can actually do this randomization in our SystemVerilog code. So one common way is through classes. So an example here is the class packet. So there's going to be a header, and then we could add effectively an infinite number of member variables in this class that we can either define as rand or not rand. If it is defined as rand, then if we call .randomize, then it's going to effectively randomize that variable. If it's not defined as rand, it will be untouched. So then that's how we can um, cause our packets or just our data sets to be modified in very specific ways. One common way that I really like to use randomization is just using the std : randomize in that middle picture there. So the reason why I like using this method is because it's very simple. It will randomize the entire variable. So some cases, or some people will use urandom, which is another SystemVerilog method. But the issue that I've found with urandom is that it only randomizes 32 bits at a time. So std randomize is better for those larger data sets, especially when you're working with values that are potentially 1,000 bits wide or something like that. You can also constrain randomization. So using the width for the standard randomized method, where we can just define Boolean expressions, and then when we go to randomize our data, the data will be randomized such that it satisfies the conditions that we've set. So I'll showcase that a little bit in the demo as well. And then also we can have rand case. So on the right, you can see we have rand case, and then there's three options. There's 3 : 1 : and 4 : So those are all their weights. So adding those up, it's a total of 8 possible, or I'm sorry, the total of our weights is 8. So then X is going to be equal to 1, 3 out of 8 times. X is going to be equal to 2, 1 out of 8 times. And then X will be equal to 3, 4 out of 8 times. So then that's kind of how we can like add some specific values, but randomize their occurrences. These can be more complex, so we can set these weights to variables or even full calculations as well. One thing to add about classes is every time the .randomize member function is called on a class, it's going to run pre-randomize and post-randomize. So these are two functions that can actually be overloaded, which again, I'm going to showcase in the demo, but we can add in some functionality that we just strictly want to occur whenever we randomize the class. So a lot of the times it'll take the form of printing a statement. We can also potentially load variables with the randomized data as well. So if you don't overload them, then they will just do nothing at their base. But we do have the functionality of being able to add our own things to these randomization capabilities. So that's just a brief overview of the code. So now I'm going to go into a live demo where my goal is to showcase what this can look like in an actual test bench, and then and then we're going to run some code, or run the test bench and showcase some things. So first, in this example, I would like to cover the class that I've created. So this is class rand packet. You can see in here, I've defined a source So the source is not going to be randomized. So this is kind of mocking or mimicking a situation where our module is generating the packet and we have a one consistent source that we're always going to be coming from. The destination is potentially random, so you can use that in situations where you want to make sure that your modules that are further down the line are denying packets that are going to the incorrect place. We can randomize our error code as well. So then we can validate that our design is handling different error codes correctly in maybe different numbers of occurrences, or also different orders of error codes. And then we also just have data just for simplicity's sake. Something that I've added here that I did talk about in that last slide was a constraint block. So I've added two. There's an error constraint and then there's a destination constraint. So I've set the destination constraint in a loopback mode such that basically destination is equal to the source. So if we send a packet out, it will just come back to us. And then for our error constraint, I've basically just set some values or set some rules for this such that my error code is going to be between 10 and 80. And then also that it's going to be divisible by 0, or I'm sorry, divisible by 2. So it's going to be an even number. And then adding to this, we have our new function. So I've overloaded the new function so I can specify my source, and then also so I can specify the seed when I generate my class. So if I were to if I were to overload the pre-randomized function, then this is what it would look like. I haven't done it in this situation, but just so you can see what it looks like. And then we have our post-randomized function. So in this case, we just have a display statement that just says rand packet generated, and then it prints out the data. With that, going on to the test bench, the test bench I've created today is relatively straightforward. It's going to be a AXI verification IP that is acting as the master to a slave AXI GPIO. So we can see the AXI GPIO, which I've labeled DUT here, our design under test, and then we have our master verification IP here. So in this situation, you can really swap out your or the GPIO for any slave device that anybody or that you guys may have in your design, and then the master verification IP is effectively going to be something that we've known to be tried and true, or something that we've created to feed our design. So you can use verification IPs. You can create code and classes for your custom protocols, that sort of thing. To talk about our initial block, so we're just initializing all of our variables here. We have the standard randomized test, so I'll talk about that in a second, or I'll go over the different tests that I've created in a second. But we're going to have this STD randomized test, so that's showcasing the STD : randomize. I have a rand case test. You'll notice that I have some parameters here. So the address is just for simplicity's sake with the waveform, so that way things are easily identifiable. But then we have A, B, and C. So these are going to be the different weights in my rand case. So you can this kind of showcases how we can modify the weights real time. So A is going to have a weight of 3, B will have a weight of 4, and C will have a weight of 3. In my second rand case test call, you can see that B has a weight of 0, and then C and A have a weight of 5 each. So this is 5 just to keep things consistent with the previous example, but they could just be equal values. So it could be 1 and 1, 2 and 2, 100 and 100. So it's not going to change the outcome there. And with the rand class test, so then that's going to be utilizing this class rand packet that I've defined on the right side. So just to go over our test so we can see what this code is going to look like. For the first run, we're going to have STD randomized test data. So that's all I'm doing. I'm just randomizing the value test data and then sending it over my AXI connection. And I'm just repeating that 4 times, so it's just going to be a completely unconstrained piece of data. In the next iteration, I've set test data equal to 0, and then I've written some code with still using STD randomize, but now using the with block. So that's going to be basically creating some constraints, kind of what we saw in the slides. So in these constraints, I've said that my test data is going to be greater than my previous test data or value, but it's going to be within 100. It's going to be within 100 of the previous value, so it can increment by no larger than 100. So moving on to the RAND case test. So you can see I've repeated it 10 times just for simplicity's sake, because my weights add up to 10. We have RAND case A, B, and C. So if the value is A, we're going to see 00D code. If it selected B, then we're going to see dead beef. And then with C, we're going to see 1, 2, 3, 4, 4, 3, 2, 1. And then it's just going to send that data and print it out. And then here for our RAND class test, so I'm going to create my new packet, and you can see I'm providing a seed. So that's 1, 2, 3, 1, 2, 3, 1. So with this, so I'm repeating it 3 times, and I'm just calling C randomize. So then it's just going to send the data packets as it normally would. So because source and destination are 16 bits each, but this AXI bus is 32, I've grouped them together. The error code is 32 bits, and then data is 64 bits in total. So I've split it into 2 prints, or I'm sorry, 2 transactions. And then in this second call here, you can see I'm running C equals new again. So I'm reinitializing the class using the same seed. So this is showcasing how you can use randomization for repeatability. So even though I've already gone through these randomized values, I'm willing to bet that in this situation here, I'm going to see the same values being output, and we'll cover that when I run the code. So then going through my class, so I'm disabling the randomization mode for some variables. Sorry, I can't get there. We go. So for error code, I'm saying that I don't want to randomize error code anymore. So that's using the .rand mode with the value 0. My error constraint, I'm turning the constraint completely off by using the .constraint mode function. And then also I'm just setting my error code to 0. So this is kind of simulating a situation where we've already tested all of our error situations, and now we want to start testing valid situations. And then also I'm turning my destination constraint off as well. So now destination is not going to be equal to source. It will be equal to any random value. And then I'm just going to randomize the data here again and just print things out so we can see how that's going to modify things. So with that, I'm going to go ahead and run the simulation. So I'm going to go up to Tools, click Run Behavioral Simulation, because that's what this is. Again, this is a relatively straightforward test bench. These things can take some really complex forms. Your RAND cases can actually also have basically decision-making processes in them. So you can use RAND case to create large trees of randomization that will all go through a decision-making process. So here's our first randomization. Just to zoom in, we can see that we have AC 2FB 7B6, and then going all the way to DB 70C51F. So if you look over these data values, which are also printed down here in the Tickle console, because I know that the Tickle console can be much easier to read, as I was talking about, we can see that these values really don't have any correlation with each other. They're just completely random. So this is, again, going to be the unconstrained standard randomize calls. So going on through the test bench, if I run this again, we can see that although I'm still, and just to showcase here, this is the randomize function that was called now. We can actually see that the data is constrained, and it's very predictable. So it's starting out at 36, 98, 159, and 211. Test data is actually 32-bit value, so it has the range of, I believe it's 1 billion different numbers that it could possibly be. So for it to be within 211 after 4 randomizations, that kind of showcases that our constraints are functioning correctly. So you can use this to your advantage. And you can also randomize multiple values at once as well, and then um, to uh, set relations to those randomized values together, such that one is always bigger than the other, or maybe one is always a product of, um, like maybe test data is always equal to um, num times 10 or something like that. So then we can create some even more deterministic things there. So then again, we can see the values that we just saw in our Tickle console being printed out here. So 24, 62, 9F, and then D3. I've printed here in decimal to better highlight the relation of the values. So then moving on through our test bench, we're now going to see the RAND case situation. I've printed out the weights here. So we have A is equal to 3, B is equal to 4, and C is equal to 3. So seeing that A is equal, or the product of A is 00D code, we can see that we have that 1, 2, 3, 4 times. With B, it being equal to dead beef occurs 5 times actually. And then C being equal to 1, 2, 3, 4, 4, 3, 2, 1, that only occurs once. So although we've provided weights, we're not guaranteed to see these probabilities over small test cases. So when you get into your larger data sets with thousands or millions of data points, you are going to see some commonality between all of this, and your weights will really show through. So just highlighting that there. Moving on to the next example, we've now run it where B has a weight of 0. So theoretically, we should never see B. Now let's see if that's happened. D code being the value that is equivalent to A in this situation, which has a weight of 5, we can see that it does actually occur 5 times, which is wonderful. And then C being equal to 1, 2, 3, 4, 4, 3, 2, 1. We wanted to let it shine a little more, so we gave that a weight of 5. So now highlighting that, we can see that it does occur 5 times, which is just kind of showcasing how maybe in some situations you just want to turn one capability completely off and you don't need to completely restructure your code. Finally, going to the last example with the classes. So now we're going to see that rand packet has been generated. Our source is equal to 1001, which is how I've defined it when I've created my packet. Our destination, again, is going to be equal to 1001. Our error code is going to be equal to 22, 64, and then 78 through our 3 randomizations. And then data is just a completely randomized value that is totally unconstrained. But if we go to our rand packet, we can see that our error constraint is that error code is greater than 10, less than 80, and divisible by 2. So we can see that we have all odd numbers and they're all within that range we've specified. So now going to our reseeded, so I created a new object, but I provided the same seed as previously. So this is later in the test bench. I should have theoretically seen another data set, but because I provided the same seed, I'm going to see the same values, and you can see that that's reflected here. So we have 22, 64, and 78 for our error codes, and then our data is ending in E8, 13, and FB. So the probability of us getting a 64-bit value repeated 3 times over is infinitely small. So I'm pretty confident to say that our constraints, or that the randomization was repeated. Going to the last example, now just to go over, or just to repeat what this last example is, I'm disabling the randomization of our error code. I'm setting it to 0, and then I'm also disabling the destination constraint. So now I can theoretically send my packet anywhere I'd like. So then running that here, we can see that my source is still 1001 because it's not defined as a rand variable. My destination is equal to 272C, 212E, and then 41F, or I'm sorry, 4EF1. My error code is always 0, and then just like before, my data is a completely randomized value. Now going to the waveforms, zooming out, we can see that all of these transactions have happened. It's just been a simple click. This code is much smaller than if I were to be writing all of these data points myself. So it's just really highlighting how quickly you can get a test bench up and running with large data sets just by using randomization and a small amount of work. So that's actually the end of the demo. So now I'll just be moving to questions. Um, yeah, thanks for watching the demo, and I will pull up the Q&A slide.
Thanks, Cole. So if folks in the audience, if you guys have questions for Cole, now is your opportunity to ask them. So just go ahead and drop them in the chat panel. I will remind you at this time that we do have 2 classes coming up that Cole is teaching. One is the Verilog class, and that is in a few weeks. And then later in October, we have SystemVerilog. So if you're interested in learning more from Cole, those are a couple-day classes. So he will be teaching those. So Cole, we do have our first question. What is the purpose of the error code?
Yeah, so the error code was just there to kind of act as a way for me to highlight different methods of constraints and that sort of thing. So it's just being an extra data point, and then allowing me to showcase disabling randomization for a variable, and then also disabling the constraints, because there is a relationship between your variable value and a constraint, regardless of randomization. So when you disable randomization of a variable and you set it to a value, if there's a constraint that conflicts with the value that you've set it to, it will the test bench will complain, and depending on what simulator, it can handle it in different ways. So it's important that you kind of make sure you're covering all of your bases with that. But really the purpose of that class that I had written was just to highlight a very simple example of something that a lot of people in this field deal with on a day-to-day basis, such as packetized data. So just trying to give some context to the example.
All right, do we have any other questions? And while we're waiting, we do have that BOGO code going on. So if you have questions about that, you can reach out to us at training@bltinc.com. That does run until October 15th. And then we also have our webinar series and workshops coming up. So the workshops are 4 hours long. Webinars like this one are 1 hour long. So you can check out the links that I put in the chat panel if you're interested in those particular upcoming events. All right, we'll wait just a few more minutes if anyone has any other questions. And then if not, then Cole, we really appreciate you sharing your knowledge today and going through the demo. All right, well, we appreciate you guys joining us this afternoon. Oh, we have there is a question about whether or not there will be a copy of the presentation. We will send out the recording. There will not be any slides provided with the recording. So that recording will take a couple of days to process, and once it's ready, I'll send it out via email to you. All right. Thanks, guys. Thanks, Cole, for sharing your information today. We really appreciate everyone for joining us, and please do look for those emails coming from me later. I will send out the recording as soon as it's ready.
Awesome. I appreciate you guys. Yeah, thanks for watching the demo.